So in these slides, we are going to be talking about the t-test and how to use it and when to use it. T-tests are used for quantitative variables. So in this case, our quantitative variable that we're interested in, so quantitative variable. The one that we're interested in today is the FICO score for this particular problem. The Fair Isaac Corporation, FICO, credit score is used by banks and other lenders to determine whether someone is a good credit risk. Scores range from 300 to 850, with a score of 720 or more, indicating that a person is a very good credit risk. An economist wants to determine whether the mean FICO score is lower than the cutoff of 720. She finds that a random sample of 100 people that had a mean FICO score of 703 with a sample standard deviation of 92. Can the economists conclude that the mean FICO score is less than 720? Use alpha equal to 0.05. So in this case, we will write down, here's the hypothesis that we're interested in. We know what x bar is. X bar is 720, or 703 actually. Mu is 720. Sx, right, we don't have the population standard deviation, so we have to use the t-test, is 92, and n is equal to 100. So we want those pieces of information before we start calculating the test statistic. The test statistic in this case is t, and I always write it down, x bar minus mu divided by Sx divided by the square root of n. Had we known the population standard deviation, we would have used a z-test instead of a t-test. So t in this case is equal to 703 minus 720 divided by 92 and the square root of 100, which is 10. So we find that t is equal to approximately 1.847. Well, the degrees of freedom here, if we went to a table, a t-table, we would say the degrees of freedom is approximately 100, because 100 minus 1, even though it's 99, we're not going to find an accurate p-value from any of the tables that we have access to. So what we do is we go into the table at 100, at degrees of freedom of 100, and see where the number 1.847 falls. And then at the top of the table, there is probabilities. So when we go to the table, we find that the p-value is 0.05. Well, actually, let me do this correctly. It's between 0.025 less than the p-value less than 0.05. So from the table, we can get a range of probabilities. But in this case, what I actually ended up doing is I put it in my calculator, and from the calculator, I get a p-value equal to 0.0338, right? So when we put it in the calculator, we do what's called a t-test. We go over to test, we hit the stats key, we go over to test, we put in our statistics, and then we use, we go down to where the alternative hypothesis is mu is less than mu naught. And when we hit calculate, we get the value of t, and we also get the p-value. So now the question is what is our decision, right? So what is our decision? Well, our decision is since the p-value is less than 0.05 in this case, that's alpha, we reject H naught. So our conclusion is based on the sample the mean FICO score is less than 720. So, and then we usually calculate a confidence interval. Our confidence interval in this case, when we do it on the t-interval, we get 684.75 to 721.25, and that's a 95% confidence interval. And the reason we use 95 is because we're using alpha is equal to 0.05. Okay. Now the question is okay, well it's between these 2 points, and yet I'm testing the hypothesis at 720. Why then is it rejected? Well, it's rejected because we're only looking at a one-tailed test scenario. And when we do the t-test, or the t-interval, we get a two-tailed test, and what happens is our confidence interval is slightly larger than our actual test. So the test is a little bit more robust, but even with the confidence interval, you can see that 720 is at the top end of the 95% confidence interval. So it's kind of unlikely to occur in most cases. So now we'll go to our second problem. In our second problem, again, we have a quantitative variable, but we have an actual data set. And when the data sets are small, chances are probably pretty good that we don't have the information on the population standard deviation. If we did, we would use a z-test, but again, we have to be very, very careful. So let's look at this problem. This is when a new when testing a new drug, scientists measure the amount of active ingredients that is absorbed by the body. In a study done at the Colorado School of Mines, a new fungal medication that was designed to be applied to the skin was tested. The medication was applied to the skin of 8 adults. 1 hour later, the amount of active ingredients absorbed into the skin was measured and is outlined in the following table. So there is the table. There are 8 different measurements from a random sample of adults taking the antifungal medication. And so part A, it says, since n is less than 30, we need to check to see if the sample is approximately normal. To do this, we usually use a box plot. And here I've shown off of the TI-83 or 84, the current box plot. There are no outliers, and the box plot looks approximately normally distributed. So now we can continue on with the test. Also, if we were using Excel, we would find what the skewness is, and if the skewness was between -1 and 1, we would say it's approximately normal, and we would go from there. Now, we want to perform the test, right? So the question is, here we want to know perform a hypothesis test to determine whether the mean amount is absorbed is less than 3 micrograms. Use alpha is equal to 0.05, right? So let's set up our hypothesis test. Our hypothesis test, H naught, right? Mu is equal to 3, and H1 is mu is less than 3. Okay, so now from our calculator, we obtained the following information. X bar is equal to 2.53. Sx, right, was equal to 0.917, and of course n is equal to 8. We're going to use a test statistic t, so we write that down. T equals x bar minus mu divided by Sx square root of n. T in this case is equal to 2.53 minus 3 divided by 0.917 divided by the square root of 8. And we get T to be approximately equal to a negative 1.4496. Now, if we're doing this by hand and we're going to a t-table, right, we need to know what the degrees of freedom of. The degrees of freedom here, since it's a small sample, is 8 minus 1, which is equal to 7. So there are t-tables that have degrees of freedom of 7. When we go to the table, though, we can't get an exact p-value, but what we can do is get an approximation. So the approximation we find from the table at 7 degrees, and you notice that this is negative, so the table actually goes only to positive values. So we make this a positive value, and from our table we have the following p-value. It's between 0.05 is our p-value to 0.10. Now, we actually do this on the TI-83 because it makes more sense to get an actual p-value. And in this case, our p-value is approximately equal to 0.0958, right? Okay, and so our decision is right, since our p-value is greater than alpha, right, we do not reject. note here that the p-value is 0.0958, and that is greater than 0.05. So 0.0958 is greater than 0.05, and that's why we do not reject, right? So what is our conclusion? Our conclusion is there is not enough evidence to determine that the drug absorbed by less than 3 micrograms. Okay? And there's not enough evidence. And the reason we say not enough evidence is because we're always afraid of committing a type 2 error. And so that's why we say there's not enough evidence to determine that the drug absorbed by the skin is less than 3 micrograms, right? So that concludes the two types of problems we will see in this chapter. And then I have one more set to do, which is the qualitative variable. And I appreciate it. Thank you.